Hi, today we're going to be talking about lesson 4-3, concavity, inflections, and the second derivative test for relative extrema. In this video, we will mostly be focusing on concavity and the basics of concavity, the graphical notion of concavity. In the subsequent video, we'll be talking about how to find that analytically and algebraically, and in the final video, we'll be talking about the second derivative test. So, in this video, let's start off by talking about a graph with this shape. And just to highlight what I'm talking about, we're talking about this upward shaping parabola. And down here, we'll be talking about this downward facing parabola. So, a graph with that upward bowl shape, a parabola type shape, is called concave upward. The tangent lines for a concave upward shape will always be below. We have this tangent line, and this tangent line. So, in terms of action, we'll go from light blue to a darker blue horizontal line to a deep blue positive slope line. So this line has a negative slope, this line has a slope of 0, then it finally becomes a positive slope. Whereas on this picture, we start off with a positive slope, then we have a horizontal slope, then we have a negative slope. So the idea is that here, the slopes, the number that would measure the slope is going from a negative value toward a positive value. Even locally, we're going from a negative value to a less negative value, or from a positive value to a more positive value. Whereas concave downward, where the tangent lines live above the graph, the slopes of the tangent lines are decreasing. We're going from a positive value to a 0 to a negative value, from a positive value to a less positive value, from a negative value to a more negative value. Why does this mean that the second derivative is greater than or equal to 0? Well, if something is increasing, if f is increasing, then f prime is positive. That's what we learned yesterday. Or sorry, that's what you learned in the videos for 4-2. So if f prime, if the slopes of f are increasing, then the derivative of f prime would be greater than 0. And that's all. If something is increasing, it means its derivative was positive, or at least non-negative. So if f prime is increasing, if the slopes of f are increasing, then f double prime is positive. Likewise, down here, if f is decreasing, then f prime was supposed to be less than or equal to 0. So if f prime is decreasing, if the slopes are decreasing, then f double prime was 0. Less than 0, I'm sorry. So that's a key fact. We will associate concave upward with a positive second derivative and concave downward with a negative second derivative. Okay. Here's a non-mathematical memory device for that. Concave upward, we're talking about a positive second derivative, which we're talking about smiley face, because smiling people are positive. Get it? Smiley. Concave downward, f double prime being negative. Negative people are frowning. Okay? Negative. These kind of look like scary pictures to me. So, a point on a graph will be called a point of inflection if two things are true. A, the graph has a tangent line, meaning the f is differentiable. And remember that being differentiable means we are continuous, means we have no sharp turns, and means we have no vertical tangent lines. Continuous means no holes, no jumps, no asymptotes, vertical asymptotes. That's all packed into that one word. You have to memorize it all. Furthermore, not only is f differentiable, but the graph changes concavity at that point. So changes from f double prime, changes from positive to negative, or from negative to positive, which is the same as saying f changes from, and we'll use the abbreviation C dot U for concave up to C dot D for concave down, or from concave down to concave up. A third way of saying it is just f double prime changes signs. It's much less restrictive than increasing decreasing behavior. So on this graph of y equals x cubed, this is a point of inflection. We are talking about a concave down shape transitioning to a concave up shape. It could be vice versa. That's the point of inflection. A graph, you could try to answer these questions on your own if you haven't already. So we're going to look for concave upward. We're looking for an upward parabola type shape, either side of it. A key idea here is that you can be concave up and decreasing. You can be concave up and increasing. You can be concave down and increasing. You can be concave down and decreasing. Both types have both behaviors. So right now, I'm going to look for concave upward. This interval is definitely concave upward. So starting from -2 and going to -1. I want to be very clear that in this lesson, I tried to emphasize it in last lesson, all of your intervals need to be open. Full stop. If you don't write open intervals in this lesson, you will lose points. Then it looks like we're maybe a downward shape, and then we're back to an upward shape. That stops right here. And we'll make it clear why in a second. So from +1 until +3, we are concave up. Something happens. And then from +4 to +5. There are no other areas where we are concave up. This is an area where we look like a downward facing parabola. We'll call that concave down. From -1 to +1, still open, parentheses, as well as this area, concave down. 5 until 6. No concavity. We're talking about no concavity for those few places where this function, this picture, this graph, has straight lines. This is a straight line from 3 to 4. This is a straight line from 6 to 7. So no concavity, we're talking about a straight line. Because it means the second derivative is always 0. for a long time. I'm not even going to write that, sorry. It's going to be confusing. F double prime can equal 0 for a moment, but it cannot equal 0 for more than a moment without resorting to a straight line. The slopes here are not changing. The slopes are not changing. That's better. Points of inflection. There's no way to write this other than with the same notation. So where does this graph have a differentiable point where the graph changes concavity? So let's look at the changes in concavity. We have one change here, but I hope you see that that is a very sharp turn. So we will not call that a point of inflection. Here, that's a good point. So 1, 1. Very confusing. It looks the same as that. Now we look for other points. Here, that's smooth, but there's no change in concavity. We change from concave up to no concavity. Here, no, sharp turn, not differentiable. Here, short. That's 5, 1. What about here? I would say it's both a sharp turn and we don't really change concavity. We change from concave down to no concavity. But really the sharp turn, non-differentiable issue is much more important. And that's the graphical notion of concavity. So in the next video, we will discuss how to do this analytically, which will give us a much more powerful technique when we have an equation of a line. So at this point, you could do questions 1 through 4. On page 70. So try those out. Make sure you can answer all those questions. Good luck. Have fun. Talk to you later.